Okay, the region bounded by y equals sine of 2x and the x-axis between x equals 0 and x equals pi over 2. We're going to revolve that around the x-axis. Okay, so sine of 2x, well, the sine of 0 is 0. If I plug a pi over 2 in, that's the sine of pi, which is also 0. Plug in pi over 4, that's the sine of pi over 2, which is 1. And then halfway between, I have changes in concavity. So this looks something like that. And I'm going to rotate that about the x-axis. So I'm going to draw a representative rectangle. Pick a random spot along the x-axis. We'll call that x sub I. And I'm going to draw a rectangle. Rotate that about the x-axis. It's going to sweep out a disk that has some width delta x. And the radius is just the height of this rectangle, which is sine of 2xi. So the volume of my disk is pi times the radius of the disk, which is sine of 2xi squared, pi r squared, times the thickness, delta x. So the volume of all the disks, I'm just going to add up all the disks that have this same volume formula. And I'm going to rewrite this as sine squared. And I is going from 1 to n. And then the volume exact is just the limit as n goes to infinity of the sum of all the disks. That is the definition of an integral. Translate by dropping the subscript i's and change the delta x to a dx. So this is pi times sine squared of 2x dx. And my bounds of integration, I have rectangles that I'm sweeping around the x-axis to form all these disks. I'm stacking up these disks starting at x equals 0 and going to pi over 2. 0 to pi over 2. Okay, last one. The region bounded by the curve y equals square root x and y equals 0.1x between x equals 0 and x equals 4. So y equals square root x, so we've got 0, 0, 1, 1, 4, 2. That should be good enough. Just connect those. Y equals square root x. Y equals 0.1x. Okay, so if I plug in a 5, well, 0, 0 is on there. And if I plug in 5, 0.1 of 5 is 0.5. So that's my next point. And I'll connect those with a straight line. Y equals 0.1x. And I want the region bounded between those two, x equals 0, which is right here, and x equals 4, so right here. So this is my region that I'm going to rotate about the x-axis. So let's draw a representative rectangle at a random x value between 0 and 4. Pick this one right here. We'll call this x sub I. And I'm going to draw a rectangle at x sub I. It has a little bit of thickness, delta x. And I'm going to sweep that rectangle around the x-axis, and it's going to sweep out a washer. So sometimes it's often helpful to draw the reflection. Goes to a little past 1.5. Draw the reflection of the rectangle, and then you can more easily picture the washer. Okay, so I need the inner radius and the outer radius of this washer. So the inner radius is the distance from the center, which is the axis of revolution. So the distance from the x-axis to the bottom of my representative rectangle, the closest point of the representative rectangle. And that is on the line y equals 0.1x. So little r, my inner radius, is just 0.1x. And then big R is the distance from the center, different color, from the center, the x-axis, to the furthest distance on my representative rectangle. So this distance, which is y equals square root x, the distance from the x-axis to this point, which is on the graph y equals square root x. So big R is square root x. So the volume of my washer is pi times big radius squared minus pi times little radius squared delta x. Then I'm going to add up n of those washers and then take the limit as n goes to infinity. So the volume of all the washers is the sum from I equals 1 to n, where each washer has that volume. And then the volume exact is the limit as n goes to infinity of the sum of all the washers, which is the definition of an integral. So square root of x squared, that's just x. So this is going to be pi x minus pi times 0.01 x squared. And then my delta x becomes a dx. And my bounds of integration are going to be 0 to 4, where I'm stacking up these washers.